Fei from Shenzhen Institute of Advanced Technology. Today I will introduce our work about massively acoustic manipulation based on artificial structure-tuned acoustic field. The outline as follows. Particle manipulation refers to the trapping, transport, sorting, and assembly of micro nanoparticles. The precise particle manipulation can provide medical particles, cells, DNA, proteins with necessary tools for their mechanical, physical, and chemical properties. Compared to the micropipe and microtwither, due to the non-contact property, methods of particles manipulation based on external physical fields are dominant. Among these methods, hydrodynamic twither is simple and integration, but non-universal. And magnetic twither is non-invasive and low cost, but it needs to modify the surface of particle. An optic twither has a high resolution and it is multifunctional, but it is also thermal and expensive. The acoustic manipulation is non-contact, non-invasive, low cost, low price, and universal. So more and more scientists are devoting their attentions to it. The acoustic manipulation method can be divided into two types, namely acoustic radiation force-based and acoustic streaming-based. The acoustic radiation force is caused by the momentum exchange between acoustic waves and particles in it, and it is determined by the acoustic field profile. The acoustic manipulation based on acoustic streaming uses a vortex to trap particles. The vortex can be considered as a second-order steady flow caused by the first-order acoustic field, and the particle in the vortex can be manipulated by the drag force from the streaming. According to the available references, there are two features of current acoustic methods. The first one, it is very difficult to fabricate the transducer according to the designed complex acoustic field profile. So only the simple acoustic field can be directly generated by the transducers. The second one, only single or several particles can be manipulated. Phononic crystals are periodically artificial structures which can be used to modulate the transmitted field to control the propagation and confinement of acoustic waves. Therefore, in this study, we want to use the phononic crystal-tuned acoustic field to modulate the profile of the transmitted acoustic beam to realize the designed complex acoustic field. And then we want to use the phononic crystal-tuned acoustic field to realize the manipulation of massive particles. We first calculated the artificial structure-tuned acoustic field and acoustic radiation force on the particle. As shown in the geometry model, the phononic crystal plate has a pure flat surface and a lattice of 800 micrometers. The simulation can be split into two steps. The first step, the acoustic field was calculated by the acoustic structure modular by using COMSOL software, and the left and right sides were set to the periodic boundaries, and the other sides were set to the acoustic radiation boundaries. After that, the acoustic radiation force can be obtained by integrating the time-averaged momentum flux tensor over the surface of a particle. As shown in the relationship between frequency, we can see that the pure plane wave, as shown in blue lines, have always a positive acoustic force. It means that the direction of the force is the same to the direction of the wave propagation. But the phononic crystal plate, shown in black lines, had a negative acoustic radiation force at a certain frequency, which corresponds to the transmission peak at the resonance frequency of the plate. From the force analysis at the resonance frequency, we can see that except for the gravity and buoyancy, acoustic radiation force in X and Z direction were also exerted on a particle in the field. We can use the acoustic radiation force in X direction to align particles and according to the balance of gravity, buoyancy, and acoustic resistance force in z direction, to realize the manipulation, to realize the trapping and sieving of massive particles. According to the above simulation, we developed the following acoustic sieve system. It consisted of a transducer, a phononic crystal plate, and an XYZ stage. The particles were placed on the surface of a fetter made of PDMS, and the whole system was immersed in a water tank. From the transmission spectrum, we can see that there is an obvious resonance frequency, and we also obtained the localized acoustic field on the surface of the resonating phononic crystal plate at a distance of 100 micrometers by using a 3D acoustic field scanner. When the plate was excited at its resonant frequency, the localized and enhancement acoustic field was generated on the surface of the plate. And as the plate was close to the fetter, the particles on the fetter was aligned by the acoustic radiation force in x directions. And these particles also can be trapped on the surface of plate by the acoustic radiation force in z directions. When the acoustic power was turned off, the trapped particles on the surface of the plate were released from the surface of plate. According to the balance, we realized the sieving of glass spheres with different sizes. At 4 watts, only particles with a diameter of 70 micrometers can be trapped on the surface of the plate. And as the acoustic power was increased to the 30 watts, particles with 500 micrometers also can be trapped on the surface of the plate. We also realized the sieving of spheres with the same size but different materials. At a certain acoustic power, only glass spheres were trapped on the surface of the plate, and all the tin spheres was left on the surface of the fetter. Next, I will introduce our work about transport of massive particles. We first calculated the lateral acoustic resonance force exerted on a particle. The particle was placed on locations deviating from the acoustic axis of a Gaussian beam. As shown in the right figure, we can see that the lateral acoustic radiation force was almost negative. It means that the direction of the lateral acoustic radiation force was towards the acoustic axis. This result suggested that particles in fields will move to the locations where acoustic intensities are larger than those of initial positions. According to the above simulation, and in order to compound with microfluidic technologies, we developed the following chip system. It consisted of a cavity made of PDMS and an offset PZT4 acoustic source and a phononic crystal plate inside the cavity. The whole system was integrated on a piece of glass, and the results can be observed and recorded by a microscope. The phononic crystal plate used in this study has a lattice of 350 micrometers, and from the transmission spectrum, we can see that the resonance frequency is around 3.6 MHz, and we use the frequency band beyond the resonance to transport particles. By using the standard chemical etching, we have obtained plates with different patterns, including the following: straight lines and polylines with 120-degree corners. We also obtained the localized acoustic field on the surface of these plates at the resonance frequency. As shown in the following videos, initially these particles were placed at the locations away from PZT acoustic sources, and when the acoustic power was turned on, these particles were immediately aligned into several parallel lines by acoustic radiation force in x direction, and then these particles were transported by acoustic radiating force in y directions. Due to the confinement of acoustic radiating force in x direction, these particles can always be transported along patterns of plate. And this result suggested that with phononic crystal guided methods, particles can be transported along arbitrary pathways. And by the selection of working frequency, the switch between transport and trapping of massive particles also can be realized. The resonant frequency of the plate was used to trap particles, and the frequency band beyond resonance was used to transport particles. As shown in the following videos, we can see that there are 3 areas to trap particles. As soon as the transported particles arrived at these areas, these particles were captured on the surface of the plate by setting the working frequency as the resonance frequency of the plate. And when the working frequency was set back, these trapped particles are transported again. In summary, a localized acoustic field modulated by phononic crystal plates can be used to trap and sieve particles. And a Gaussian beam combined with phononic crystal plates can be used to transport particles along arbitrary pathways. The third one, massive microparticles can be manipulated by artificial structures.